So in the last example, we saw that, let me slide back up to that graph. We saw that when x approached infinity and your y value was a finite number, we actually had a horizontal asymptote there. Both in this 1 over x and also in the 5 over x cubed, we had a horizontal asymptote of y equals 0. And so now we want to look at the definition of a horizontal asymptote. And the definition is this. The line y equals L is a horizontal asymptote of the graph y equals f of x if either the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches infinity of f of x equals L. And so this differs from the definition of a vertical asymptote. Here, x is approaching either positive or negative infinity, and y is approaching a finite value. Remember, with a vertical asymptote, the opposite was true. X was approaching a finite value, and your y values, or your function values, were growing without bound. So the first example I want to look at here is the graph of the inverse tangent of x. And again, you should have refreshed your memory about the inverse tangent graph. You should be able to graph that by hand. And if you did, you'd know that the value right here is pi over 2, and this value right here is negative pi over 2. And so as x approaches infinity of the inverse tan function, we can see as x gets really, really large, the y values are approaching a finite value. That finite value is pi over 2. Now we're not going to hit pi over 2, but we're going to approach it. And eventually, this function will flatten out and almost look like a horizontal line. It looks like that asymptote. And so the limit as x approaches infinity of the inverse tan function is pi over 2. As x approaches negative infinity, the y values are approaching negative pi over 2. And so the limit would be negative pi over 2. Now what that means, according to the definition, when x approaches infinity or negative infinity and y approaches some L, then y equals L is your asymptote. It's a horizontal asymptote. So this function has two horizontal asymptotes, y equals pi over 2 and y equals negative pi over 2. Right, let's just go back and look at an example with a vertical asymptote. Remember the graph of tan x and the graph of tan x as x approaches pi over 2 from the left and x approaches pi over 2 from the right. And so when we look at pi over 2, as x approaches pi over 2 from the left, the y value is growing without bound, so the limit was infinity, and we had a vertical asymptote there. We also, when we approach the tangent, when x approaches pi over 2 from the right of tan x, so we let x approach pi over 2 from the right, the y values are going to negative infinity. And so negative infinity is the value of the limit, and we had a vertical asymptote at x equals pi over 2. So let's look at some of the properties. The properties of limits that we looked at as x approached some finite number still hold true as x approaches positive infinity and negative infinity. And so I'm just going to briefly go over these. You can keep these as a reference. But the limit of a sum or the limit of a difference is equal to the sum or difference of those limits. The limit of a product is the product of the limits. The special case of that is the scalar multiple or the constant times the limit of a constant times a function. You're able to take that constant outside of the limit and multiply it by the actual limit value. The limit of a quotient is the quotient of the limits, as long as the denominator's limit does not equal 0. The limit of a square or an nth root function is the nth root of that limit, as long as if you have an even root, that your limit is greater than 0. Remember, you can't take the even root of a negative number. Same thing with a function raised to, the limit of a function raised to a power. That's the same thing as the limit raised to a power. And again, as long as that limit is defined for n. So if that n was fractional and you were approaching negative infinity, that would not be defined. You can't, if it was an even root, you cannot take the even root of a negative number. Let's look at the limits of x to the n as x approaches positive or negative infinity. And let's first just look at two functions. This is an odd function, and this is an even function. And so when n is odd, and in this case n is even. And we'll first focus on the limit as x approaches infinity of x to the n when n is odd. In this case, as x goes to infinity, the y values are growing without bound. So if x is odd and x goes to infinity, then x to the n also goes to infinity. Your function is growing without bound. As x grows to infinity, when n is even, so as x gets really, really big, y again, or the function value, is getting really, really large also. So for both cases, when n is odd and when n is even, as x goes to positive infinity, your y values are growing without bound. It makes sense, because if you take a positive number, a very, very large positive number, and you raise it to a power, if you multiply it by itself over and over again, whether that's an even number of times or an odd number of times, that number is going to get extremely large. Now, it's a little bit different when you're approaching negative infinity. And so let's look at this picture right here on the left, the odd function. When x goes to negative infinity, when x is getting really, really negative, your y values are getting really, really negative when n is odd. Because if you take a negative number and you raise it to an odd power, you're going to get an odd negative number. And so since these are really, really large negative numbers, this is going to go to negative infinity. So as x goes to negative infinity of x to the n, when n is odd, the answer is negative infinity. But when you take a negative number and you raise it to an even power, that is going to be equal to a positive number. And so the limit as x approaches negative infinity of x to the n, when n is even, and this is an even function right here, as your x gets really, really small, or really, really negative, your y values are getting larger and larger. And so you learned about this you should have learned about this or seen this in an algebra class or a pre-calculus class, and this is basically about end behavior. When we talk about end behavior, we're talking about the value of a function for extremely large positive values of x or extremely large negative values of x. And so let's look at example 4. Without having a graph, let's evaluate these limits. So the limit as x approaches infinity of x cubed, if you take infinity and you multiply it by itself 3 times, you're going to get infinity. As x goes to infinity, whether your exponent is even or odd, the value is going to be infinity. The limit as x approaches infinity of x to the 4th, that's also going to be infinity. You have a positive base and an even exponent, you're going to infinity. As x goes to negative infinity of x cubed, you have a negative base and an odd exponent, so that's going to be negative infinity. The limit as x approaches negative infinity of x squared, you have a negative base and an even exponent, that's going to be positive infinity. And as x approaches negative infinity of negative x cubed, well, if we just first focus on negative infinity cubed, that would give us negative infinity. But the opposite of negative infinity would be positive infinity. What might help you in evaluating these is writing the end behavior for each function. So underneath, I'm going to write the end behavior. For an x cubed, the end behavior looks like that. It's down to the left and up to the right. For an even exponent, it's up and up. For an odd exponent, again, it's up and it's down. For an even exponent, it's up and up. And for an odd exponent, where you take the opposite of it, you're actually going to be up and down. And you can use these ideas or these arrows to help you determine whether it's going to be positive or negative infinity. So this brings us to the next idea, and that's the end behavior of polynomials. The end behavior of a polynomial matches the end behavior of its highest degree term. And so in pre-calculus or an algebra class, you should have learned that when you're dealing with end behavior, you only need to worry about the largest, the term with the highest power, or the highest degree. Because what happens is that eventually takes over. As x gets really, really large or very, very negative, that takes over and these other terms become insignificant. So let's evaluate the limits in example 5 and example 6. We have the limit as x approaches infinity of 4x to the 5th minus 3x cubed plus 10. We know that the leading term takes over, so the value of the limit is going to be the same as the limit as x approaches infinity of 4x to the 5th. I'm allowed to take 4 outside of my limit. Later on you can actually do this in your head. I'm going to have 4 times the limit as x approaches infinity of x to the 5th. This is a positive base, and if the base is positive, if it's positive infinity, no matter what the exponent is, this is going to infinity, if it's a positive integer. So 4 times infinity is going to be infinity. Let's look at the second one. We know that the limit of a polynomial as x goes to infinity or negative infinity is the same thing as the limit of the leading term. We have negative 5 times the limit as x goes to infinity of x squared. We're going to have negative 5 times whatever the limit of as x approaches infinity of x squared, that's going to be infinity. So a negative 5 times infinity is going to be negative infinity. So your end behavior for the first function would have been a down and an up, and since we're going to positive infinity, as x goes to positive infinity, y is going to positive infinity. The end behavior for the second problem is down and down. So as x goes to positive infinity, your y values are going to negative infinity.